Welcome, class. Good to be with you again. This is going to be on Chapter 6, Whitlock and Schluter, an Intro to Hypothesis Testing. And I want to just start off by looking at the scientific method. And I have "the" in quote marks because if you take a philosophy of science class, then we see that there is no "the" scientific method. Nevertheless, it's often summarized as we make observations. Based upon those observations, it could just be from the world or possibly theory. We'll set up a hypothesis and then formulate some type of experiment in order to test that hypothesis and analyze those results. Now, in modern science, this hypothesis section, as well as design of experiments, has pretty much been taken over by statistics, and the lingo is particularly statistical. And that may be something that's very new to you, but we're going to introduce these concepts today. So to lead into this, I'd like to look at Proverbs 1, first 7 verses. It starts talking about to know wisdom and instruction, to discern the sayings of understanding, and it moves in this line, introducing the book. And then the theme verse, which parallels chapter 9, verse 10, check it out. The fear of Yahweh is the beginning of knowledge. Fools despise wisdom and instruction. Notice that everything rotates around this fear of Yahweh. That's the realm within which the entire enterprise operates. By contrast, in the scientific method, we have just observation, hypothesis, experiment, analysis, and then repeat. You've got a naturalistic process, human-centered. So I want to contrast the biblical mode, and I want to operate that in that as we proceed. Okay, so that being the case then, let's get into it here. Hypothesis testing. Neat history. I won't read all this, but Jerzy Neyman and Egon Pearson are the two guys that are credited with breaking the ground here. And Jerzy was a Polish Catholic. In Poland, he read the writing on the wall before Hitler invaded and got out. Wealthy, educated, and guess where he came? California. Berkeley, and he became a prof at UC Berkeley's statistics department. Okay, but in the 20s, he studied for a time in London, and he met up with the son of Carl Pearson, Egon Pearson. Remember, Carl Proud formed the first statistics department in the country. So his son is kind of under the thumb of his dad, not allowed to teach and stuff. But he wants to come into his own as a statistician. And so he meets up with Jerzy Neyman, and they formulate the foundation of what becomes hypothesis testing. And so he really is able to break some real ground that way. And that's a neat background and story. Okay, into hypothesis testing then. The idea is simply this. There's a quantifiable hypothesis, okay? Once we get that hypothesis, we then do collect the data. There's a technical distinction between an experimental and an observational study, okay? Classically, they just did the best they could, okay? And then once you do that, you do the analysis on the data. We get the statistics, and then we're going to see what that says about the hypothesis. So here's the key thing. It turns out that when you set up your hypothesis, there's actually two, and there's going to be always and only two hypotheses. That's part of the statistical distinction, the null and the alternative. Once we get those things set up, then we compute the test statistic. Okay? We're going to compute the evidence for or against H null. We're always talking about the null hypothesis. That's sort of the hypothesis, if you will, even though there is an alternative running around. And once we run up with that evidence, then we make a decision. Do we reject the null hypothesis or not? Okay, let's talk about these two hypotheses. They're mutually exclusive and they're jointly exhaustive. What that means is, in your population, okay, I'm not looking at a sample now, I'm just looking at the population. Let's suppose that there's an unknown mean, okay? Then we divide that population into two groups, okay? There is a null hypothesis with one group, okay? And then there's an alternative hypothesis. Okay, so you might just have some mean here in the null, and then the alternative, it could be, it's some other range of the mean. So maybe let's say mu greater than 5. Maybe here, this is mu equals 5 in the left-hand side, the null. Okay, so that being the case, the null hypothesis is what we call the nothing happening hypothesis. This is my favorite. Nothing is happening. Whereas the alternative hypothesis, that's the something happening. Our text, Whitlock and Schluter, don't say it that way. But you'll notice that that's what things look like. You might see in our text difference, whereas in the alternative, there's, in the null, there's no difference. Nothing's going on. Whereas in the alternative, there is a difference. Okay. And let's see. Under the null, that's the not significant result, which means there's no discovery. We wouldn't get the journal published, we wouldn't get the patent, and so on and so forth. On the other hand, for the alternative, that is the significant result, and that's the one where we do make the discovery. Okay. I like to say in the Latin, the null hypothesis is just the status quo, whereas the alternative is the nouveau. Okay. French. And from the technical standpoint, the null hypothesis is, we'll add one more line, it's always assumed true. Whereas the alternative hypothesis, this one is going to be the one that we must show. Later we'll see that it's like the null hypothesis is innocent until proven guilty, in which case we go with the alternative. Okay, so that covers these first few. Now, this chapter is an overview of hypothesis testing. We're not going to get into specific details, so just keep that in mind. In fact, it may leave you somewhat uncomfortable because there are certain things that we're not making explicit. Feel free to bring those questions to class. Okay, I'm going to look at a common one. We might have a null hypothesis where there's a certain proportion set at 90%. Okay, maybe we're talking about free throw percentages. If that were the case, then perhaps the alternative would be, okay, he's not a 90% free throw shooter. That's a simple example. We could have a hypothesis that the average Biola student height is population mean equals to, let's say, 67 inches tall. Okay, we have a lot of women on campus. The alternative may be that the mean is not equal to 67 inches tall, something else. All right, that's two explicit examples quantitatively, although I've stated what they are verbally. Now, let's go on to the sample statistic. Okay. The sample statistic is going to be calculated from the data, and what statistic we calculate depends upon the form of the data. And that's determined in the hypothesis, and we'll look at that as we go. It's always going to be a single number. Okay, so in the examples that I looked at, the basketball proportion example, we might have a sample statistic of p hat. Let's say they turn out to be 87.1%, so let's put 0.871. Okay, whereas in the height, let's suppose that we come up with a sample mean of 69.2 inches tall. Okay. Way over what we hypothesized. Those would be two sample statistics. Now, using that sample statistic, there's a thing that we calculate called the evidence, or the p-value. Now, we don't have any equipment to do this, but what's going to happen is, if you sketch the distribution, this is where that famous bell-shaped curve is going to come in, as we'll show in Chapter 10. If the true proportion is 90%, as we hypothesized, then if that 0.871 is way out here, then it's considered very unlikely, okay? And so we're going to wind up rejecting the null hypothesis. If there's really a 90% chance, then it's unlikely we would get our data. Therefore, we conclude this is not really the true proportion. On the other hand, if the 0.871 winds up here, then you can tell that that's pretty likely. That's going to happen at greater frequency. And so we would be inclined to say, yeah, this 90% is reasonable for us to get this kind of data. So that would work. And again, with our heights, the same idea would obtain. We're hypothesizing a 67-inch. Data comes in at 69.2 inches. Well, if it's far away, way at the top of the curve, that would be unlikely, so we would reject the null hypothesis. On the other hand, if it's near, maybe the 69.2 mapped here, then we would not reject the null. And I'm fine with using the language except the null, despite what the book said, and we can talk about that in class. Okay, that's the p-value. So you can interpret the p-value as the probability that you observe your statistic or worse, given that the null is true. And that's just what I depicted in these two diagrams. Okay, an alternative is this definition. It's equivalent but alternative. It's the probability that the test statistic is the result of sampling error. That means, in this case here, the distance here of my sample stat, this is p hat, whereas this one's p, keeping in mind my original map population. True proportion is p. Inside the sample, I get a p hat. That's the summary of my data. That difference there is merely a result of sampling error. Okay? If it's a reasonable probability, then we're going to accept the null. If it's an unlikely probability, we reject the null. Okay, got it. Now, using the p-value then, this is pretty much what we're going to do. If the p-value is below some threshold, then we're going to reject the null hypothesis. If the p-value is greater, then we say, technically, I'm going to write this out so I don't get in trouble, do not reject. And in class, a lot of times I will say accept the null hypothesis. If we reject, that's when we've something happening that's called statistically significant. That's a technical term. If we do not reject, then the test is not significant. Okay, pretty much covers it. We're going to use this thing right here called a level of significance. It's the Greek letter alpha. And so if we had a level of significance, let's just come up here. Perhaps if it was right here, a lot of times we use 0.05, 5%. It's a probability or an area under the curve. Then on this value, I would reject. On this value here, I would accept, because my probability here is greater than 0.05, whereas here it's less than 0.05. And again, we're going to see this later, so you don't have to fully grasp it all right now.